Hello again, physics friends. Today we're going to be practicing how to use the effective potential and how to interpret the effective potential. Before we get into that, though, I want to take a look at a system that you know and love, the Earth in orbit around the Sun. So if we have the Sun here, and we have the Earth over here, and the Earth is going to be orbiting the Sun, we know that there's a bound system in a nearly circular orbit. And in principle, you could have a perfectly circular orbit under the force of gravity. Okay. Now, how does this come about, right? If we make a plot of the potential energy due to gravity, which we know to be g times m times little m over r to the first power with a minus sign. So that if we have two masses, let's say the Sun is mass big M and the Earth is mass little m, this quantity, this potential itself does not have a minimum, right? It's a monotonically increasing function that starts at negative infinity for r close to 0, and it continues up. It approaches 0 as r approaches infinity, and so the potential energy associated with gravity is everywhere negative, according to this formulation. So this plot is u of r for gravity. And what we know when we looked at potential energies and the graphs of potential energies, we found that we could talk about bound systems or unbound systems. We could talk about circular orbits or periodic orbits and so on, but there's no minimum of this potential. So that would suggest that there's no circular orbit, right? Because there's no energy, there's no state of the system for which r doesn't change. And yet we clearly know that there is circular orbit. So what's going on here? Well, the thing that's going on here is we're treating this as a one-dimensional problem, and nothing in this plot captures the fact that the Earth can move in 2 dimensions, right? The angle in polar coordinates can change, and that is not at all captured here. So that's exactly the goal of this, the centrifugal potential and the effective potential as the sum of the potential associated with a force and the centrifugal potential. So if you recall, the effective potential has 2 pieces. The first piece deals with the constant angular momentum, and the second piece deals with the potential of the force at question. So if we're talking about a gravitational system, then the second potential would be the gravitational potential, but we have to add to that this 1 over r potential. 1 over r squared. This should be 2 mu r squared in the denominator. So we've already drawn the gravitational potential in purple. I will draw the 1 over r squared potential in blue. And that looks like this. It asymptotes to 0 as r gets large. And when you add these two together, you get the total effective potential. Okay? And the effective potential starts positive, dips down below 0, and then follows the purple curve largely. Okay, like that. So this curve here, the black curve, is the effective potential. And now notice that this effective potential does indeed have a minimum, so there is in fact a specific value of r, an equilibrium value of r, that corresponds to a circular orbit, like so. Okay, so I just want you to think of the effective potential as a way to capture both the potential associated with the force and the fact that the system has an angular momentum, L. In other words, the fact that the system is moving in theta or in phi, depending how you like to label your angle. So what we're going to do now in this video, for the rest of this video, is work through a problem. It will not be a gravitational potential. it will be some other potential, but we're going to look at the effective potential, talk about whether or not there's a circular orbit and whether that orbit is stable or unstable, and if it's stable, what is the frequency of oscillation about the circular orbit. So here we'll keep this key idea that the effective potential is given by the following, and also we'll add to that the expression for the equation of motion for the 1D system, that mu r double dot is given by minus the derivative of the effective potential with respect to r, which looks like Newton's second law in one dimension, but of course hidden in U effective is not only the real potential, but also this centrifugal potential. And here I'm going to get rid of the g, so that this is in general any potential, not just the gravitational one. The effective potential is this 1 over r squared term plus the potential associated with the force. Okay, so now we're ready to look at this problem. Okay, we have two particles with reduced mass mu, and there's an interaction between them, which is a parabolic potential, right? This is like a spring force potential, where r is the distance between them. Make a sketch showing the potential, the centrifugal potential, and the effective, which is the sum of u and UCF. Okay, and here we can treat the angular momentum, L, as a known fixed constant. I'm going to call it L naught, actually. So why don't we start with that? Okay, so here we go. Here's a plot. And these are going to be potentials as a function of r. And let's start with our centrifugal potential, right, which we know is like a 1 over r squared. Draw that in blue. And then we have the potential associated with the force. That's this potential, 1/2 kr squared. That's a parabola. And finally, we'll draw the effective potential in black, which is the sum of the two. So on the left side of this plot, the purple curve is small, so the sum will just basically equal the blue. And on the right side of this plot, the blue is very, very small, so the sum will just basically equal the purple. And in the middle, we have a point that's right there, equal to twice the height of blue and purple because they're equal at that point. And so we have the following effective potential in black. So that's our part A. Part B is saying find the equilibrium separation r naught, the distance at which the two particles can circle each other with constant r. So remember, we have particle 1 and we have particle 2, and there's an effective potential between them. And we're looking basically for an orbit at a fixed separation between them r. And we'll call that r naught. Okay. And we're going to look for that value of r naught. Well, of course, that r naught corresponds to the place where the effective potential is flat. So in part B, we want to find slope of U effective equal to 0. That's our condition. So we need to compute the the ddr, the derivative with respect to r, of the effective potential. So what is the effective potential for this problem? Okay, well, it's always going to have this L naught squared over 2 mu r squared. And then we're adding to that the actual potential associated with the force in this problem, which is the spring force potential, 1/2 kr squared. So we need to take a derivative with respect to r of that set of two terms. Okay, and when we make that derivative, we'll get a minus L naught squared over mu r cubed plus kr. So that's the spring force, k times the stretch, and this is the centrifugal force, so 1 over r cubed force. Okay, and we need that to be 0 in order to have a zero slope. So that tells us that k times r naught is going to equal L naught squared over mu r naught cubed. So from that we find r naught to the fourth power is equal L naught squared over mu k. Okay, so there is a specific value of r naught for a given angular momentum that will give you a circular orbit. In other words, these two particles move around each other at fixed separation. The final piece of this question is to say, okay, if we have a particle sitting at r naught and we give it a little nudge, or if we have these two objects orbiting each other at a fixed separation and we give a little perturbation, a little radial perturbation, that means the separation between the atoms will grow and then shrink and then grow and then shrink and oscillate it back and forth. So you kind of get this rotation along with a little vibration. Okay, and we want to know, what is the frequency of this oscillation, frequency of small oscillations about the circular orbit. Okay. Well, to do that, we can either look at the curvature u double prime in the vicinity of the equilibrium position, or we can look at this equation of motion and do Taylor expansions. Okay, so let's do both. We'll solve this problem two ways and compare our results. Okay, so for part C, we're first going to Taylor expand U effective, and so we can write U effective as a function of R as U effective at the equilibrium plus the derivative of U effective at the equilibrium times a step away from the equilibrium plus 1/2 of the second derivative times the square of the step away, and so on. And the and so on really means plus terms that are of order epsilon cubed. So those are the higher order terms here, which we are going to ignore. Okay, so notice in each of these terms, it's a polynomial in epsilon, and each of these terms is the coefficient of that polynomial. The first one depends on the zero derivative, the first derivative for this next term, and the second derivative for the next term, and so on. And what is this epsilon? Well, here we're basically taking r to be r naught plus a deviation away from r naught. So epsilon, epsilon is the distance from equilibrium. Okay, so we can look at that here. Epsilon is like a displacement from equilibrium. All right, well, we already know what the first derivative of U effective is, and we know that it's 0 at R naught. That's exactly what it means for the potential to be flat at R naught. So now we have to find the second derivative. Okay, so we need to find U double prime of R, which is dr of this term, minus L naught squared over mu R cubed, and so on. So let's compute that. Okay, so from the first term, we are going to get a minus 3 r to the minus 4. And then we end up with a k, derivative of kr with respect to r is simply k. And then we're going to evaluate it at r naught. Okay, so that gives us 3 L naught squared over mu r naught to the fourth plus k. Okay, but we know what an expression for r naught already. We know that r naught is L naught squared over mu k. Or if you'd like, we can just replace the r naught to the fourth term here. Okay, so r naught to the fourth is L naught squared over mu k. So our L naught squareds will cancel, our mu's will cancel, and we have 3k plus k, which gives us 4k. So after all is said and done, we have U effective double prime at R naught is 4k. Okay. And we know that the angular frequency squared is given by U effective R naught double prime divided by the mass of the system here, but actually the mass, by mass here we mean the reduced mass. And so this tells us that the angular frequency of oscillation will be 4k over mu. So that's how you would solve this just looking at the potential alone. But I also want to work this problem from the perspective of the equation of motion. So here's another way forward. We can start with the equation of motion. And we know that du effective dr is given by L naught squared over mu r cubed plus kr. Excuse me, that's minus kr. Let me correct that. And it's minus because this is minus du dr, so it's minus the negative gives you a plus, and minus the plus gives you a negative. And then we can use the fact that we're looking at small deviations away from equilibrium, so we can rewrite r as r naught plus epsilon. And the time derivatives tell us that r double prime is equal to epsilon double prime because r naught is a constant and its time derivative is 0. So using the purple equation and our equation of motion, we find the following. We find mu epsilon double dot is equal to L naught squared over mu r naught plus epsilon cubed plus k r naught plus epsilon. And we want this to look like epsilon double dot is equal to minus omega squared times epsilon. So we need to linearize this equation of motion, which means we need to linearize this term. So let's just focus on that one term for a moment. Okay, here we have 1 over r naught plus epsilon cubed. That's nonlinear. Okay, that's, if we factor out an r naught, we get the following, which we can write as 1 over r naught cubed times 1 plus epsilon over r naught to the minus third power. And here we can use that binomial expansion, that 1 plus x to the n is approximately 1 plus nx for x much less than 1. Okay, so in that case, the approximation becomes 1 minus 3 times that ratio. So we can bring that into here. And what we see then is L naught squared over mu times 1 over r naught cubed, 1 minus 3 epsilon over r naught. Okay, and once again, we can use our understanding of how r naught is related to L naught squared. Okay, so I'm going to replace L naught squared with mu times k times r naught to the fourth. So mu times k times r naught to the fourth, that's our L naught squared. And from here out, it's just simple algebra. We can see that we're going to get some cancellations. The mu's are gone. 3 factors of r naught are gone. So we'll have k r naught minus 3k epsilon minus kr naught minus 1k epsilon So the k r naught terms are gone. And we find mu epsilon double dot is equal to minus k epsilon. Well, that is exactly the equation of simple harmonic motion. So I can write that as epsilon double dot is equal to minus 4, sorry, that should be 4k. 3 plus 1 is 4, minus 4k over mu times epsilon. That's the equation of motion for small perturbations, and the term in parentheses is our omega squared. Okay, so that these perturbations epsilon will evolve as a cosine or a sine with some amplitude and some phase, but the frequency of that oscillation is fully specified, 4k over the reduced mass of the system. Good, so I hope that this example has given you some ideas of how to make use of the effective potential to look for stable circular orbits. Thinking of this all as a one-dimensional problem, much as we did when we first encountered potential energy graphs earlier this year. And also in finding the Taylor expansion of U effective or thinking about how to linearize an equation of motion, I hope it's given you a sense for how to apply some numerical techniques or mathematical techniques rather, to look for small oscillations about stable equilibrium positions. Good, so that's all we have for today for this example. But until next time, take care and be well.